angle resolve photo emission. So Ming, you got like an hour, and I'll flash you the time. Okay, go.
Thank you, Stephen. This is on? Oh, okay, great, thank you. I really like to thank the organizers for this opportunity. This is my first time in Spain. I really enjoy every minute of it, and the scenery, as well as learning from all the other speakers and all the students in the poster session. So thank you all very much. So I have your attention for about 2 hours today with a break in the middle, and I've constructed my talk in on 2 unequal parts. So I'm an experimentalist, and our group does mainly angle resolve photo emission spectroscopy. I will spend the first half an hour or 40 minutes telling you a little bit about the technique and some of the things that's happened in the ARPES community in the past decade or so in terms of instrumentation developments, and then spend the next hour and a half-ish talking about flat bands and bulk materials, how we study them using ARPES. So it won't be equal parts, and I will just stop around an hour if Stephen will tell me. So here we go. So please stop me with any questions. And anyway, okay. So ARPES, the technique of ARPES is theoretically very simple. We utilize the photoelectric effect. Basically, you know that when you dump photons onto a metal, and if the photons have enough energy to kick out the electrons from the material by overcoming the work function, then these electrons will fly out into vacuum, and carrying with them information about the electronic state from which they were kicked out. And so the main workhorse of our technique is this electron analyzer, and it'll pick up the electrons, photoelectrons, from a certain angle emitted from the material, and then measure the energy and also the momentum of these photoelectrons. So the technique is very simple, and then we know that in the photoemission process, the energy and also the in-plane momentum are both conserved. So if you can measure the outcoming energy and momentum of these photoelectrons, then you can back out the energy and momentum relationship of the state from which these electrons were ejected, right? So, and you know that that's a measurement, direct measurement of the electronic structure in momentum space. So nowadays, the most common type of electron analyzer are these spherical shaped ones. I'll talk about how they work in a bit. And the kind of data that we take are these two-dimensional images that have energy versus momentum, and so this is like a slice through this electronic structure, and we can only measure electrons that are occupied, so we can measure up to the Fermi level. And then you can imagine by varying the angle between the analyzer and the sample, you can take parallel cuts of these, and then from that you can construct the three-dimensional electronic structure, and then take any kind of slice you want, and including these constant energy contours, which it can be used to measure Fermi surface. So theoretically, it's very simple. If you wonder how the analyzer actually measures all of this stuff, so this is a cut open view of what these hemispherical analyzers look like. So essentially, here's the sample. Sample sits on the stage, and then we shine beam a light onto the sample, and then electrons are ejected everywhere. And so for a given geometry, the electrons on this slice make it through the analyzer. And so in the direction which is along the slice, the momentum information is actually captured. So what happens is that between the sample and the entrance to the hemispherical analyzer, there's a bunch of electrical lenses. And what they do is that they will guide the electrons, photoelectrons, into this trajectory such that you can see the angle which the electrons were emitted will get propagated directly to the angle which they hit the entrance of the slit. And then from that point on, they enter this region where the inner and outer hemispheres are put at plus and minus voltages. And that applies a field that will bend the electrons across to the other side. So you can see that this dimension is the emission angle, which can be converted very easily to the momentum. And that gets directly preserved into this direction of the detector. And then if your electrons are traveling very fast, they will land on this side of the detector. If they're very slow, they will land on this side of the detector. So therefore, naturally, we get an image on the detector that has energy and momentum as the axes, right? So this is basically how modern-day ARPES analyzers work. In reality, there are many things we have to do right to get our data properly. For example, the beam shines on the sample over a beam spot, and so all of our signal comes from whatever comes out of this spot. So therefore, we have to have a very smooth sample, because if you have inhomogeneity over the sample, then all of that gets integrated into your final signal. The other thing we have to be very careful about is that we hope that the electron will be unperturbed on their way from the sample to the analyzer, right? So that means that we have to do this in ultra-high vacuum, and as well as in a very well-shielded environment where we can shield off the electric and also magnetic field. So therefore, all of this has to happen in these carefully shielded chambers, right? So this will become important in some of the things that we'll talk about later. So essentially, this is the technique of ARPES. What do we actually measure? So this is exactly what we measure. So this photo emission intensity carries many terms. This is just overall intensity. This is known as the matrix element. Basically, this is a term that is a set of selection rules depending on your polarization of your light beam relative to the direction of your orbitals. This can suppress or enhance intensity, which can be used as a way to look at the orbital information of your electronic structure. This is the Fermi-Dirac function, so we only measure the occupied states, and then all of this stuff is convolved with the resolution, right? So the most important aspect is this A of k of omega, which is a single particle spectral function, and this has already been discussed, and I just want to also give you some sort of pictorial view of what kind of information we can actually gather from this measurement. So, of course, we measure this energy dispersion relationships. But in addition, any effects that changes your electronic states can be captured in these self-energy terms. There's a real part and also an imaginary part. And so just to show you what kind of information we can get from this, if you imagine you have a non-interacting system, I think Lenny already showed this in her talk. So you will get these essentially infinite lifetime states, which are right, that they're not interacting, and then this is the dispersion that you will see. If you start to consider interaction on the single particle spectral function, for example, in a Fermi liquid, what would happen is that you can rewrite this into two terms. There will be a part that looks like almost like the non-interacting limit. And so these are the quasi-particles near the Fermi level with some modifications. And then there's another term, which is the incoherent part, that gets pushed farther away from the Fermi level, right? So from spectral perspective, what do we see? We will see all of this stuff carried essentially simply in this coherence factor, which varies between 0 and 1, and there are two ways in which this modifies the spectra. First of all, you notice that this is the overall spectral weight modulation here. So essentially, if you have correlation, you will see a suppression of your spectral weight. And then the second part where this enters is here. It modifies the dispersion relationships that we actually observe from ARPES. And essentially, you will see that there's an overall squeezing energy of these bands. So both these ways can be utilized to gauge the strength of electron correlation effects seen by photoemission. And of course, if you keep going in the Mott limit, you get zero spectral weight with a complete flat band, and that's the Mott limit. Right. So practically, what we do, we take a new material and we measure the band dispersions. For example, this is one of the first iron nictide superconductors, and you will see these spectra here, and you can sort of make them out. And then you just slap on the DFT calculations, and for moderately correlated materials, you will realize that you can make some reasonable agreement between the measured dispersions and the DFT calculations if you renormalize or squeeze the DFT bands by a certain factor, and this factor is a quantitative measurement of this coherence factor. It's 1 over the coherence factor. So this is a direct way that we can utilize to sort of compare the correlation strength across different materials. So this is just like I think this is just a visual way of seeing what we actually measure. Okay. So there are, anything that modifies these AK of omega can be captured in our measurements. So we don't just measure the band dispersions, but we can measure a range of phenomena. For example, this is taken off this recent review of the ARPES technique. If you have a free electron dispersion that looks like this, we can, for example, look at the effect of electron boson coupling, and this will basically produce a so-called kink in your dispersions. Basically, the energy of the kink tells us the energy of the bosonic mode. These could be phonons, magnons, even plasmons. Essentially, basically, you can see that the Fermi velocity or the slope of the dispersion within the energy is smaller than the bare band dispersion. And this sort of tells you the strength of the electron boson coupling. The previous example, I sort of discussed this already. You can have normalized bands because of electron-electron interactions. And then, of course, you can. There's also spin-resolved ARPES. You can look at the spin texture of your band dispersions. And then with all of these, we can measure all kinds of materials that have been discussed this week already. So for example, ARPES has been utilized to study the spin momentum locking of the topological surface states of topological materials. We can look at the gap produced by a superconductor. These are particle Hall symmetric gaps at the Fermi level. We can also directly look at the formation of charge density waves via the measurement of their CW gaps, which are not particle Hall symmetric necessarily, but it should be gapped across the Q vector of your CDW. And then finally, we can also look at Mott insulators. This is basically the lower Hubbard band, and you can sort of look at the Mott gap, for example, directly from photoemission. So these are some examples of, if you are curious, this is a very nice review of things that have happened in the ARPES community recently. Okay, so what I want to talk to you about, I think this is a very nice perspective shown here about what has happened in the ARPES community over the a few decades. On the bottom, this is basically state-of-the-art energy resolution, also converted to the equivalent energy scale, temperature scales on the right-hand side develop over the years. And by this trend, there's hope that we will come down further in the next decade or so. But I think what's really interesting is the top plot. So the vertical axis is basically number of publications that mention ARPES over the years. What comes out of this is that the development of this instrumentation is really strongly coupled to the emergence of different families of quantum materials. You can see that this is when the Krupp-Rays was discovered, so on and so forth, all of these material families. And many of the instrumentation developments enabled the exploration of these families, and then vice versa, the properties of some of these materials also help to drive the development of certain instrumentation for ARPES. So for the next, maybe 20 minutes, I want to show you three examples of stuff that's happened in the past decade or so. This is, of course, not a complete list, but just things that I think is interesting for this community. So one of which maybe many of you are familiar with, given the interest in the Moray systems in recent years, is the development of nanofocus beam. Remember, this is basically this is the limiting factor of how small a sample we can measure. And that, together with what's called the deflector mode, really enabled the measurement of exfoliated flakes and Moray materials and so on and so forth. So what's shown here is I took it off the website of Maestro Beamline, which is a nano-ARPES beamline advanced light source in California. This is a real space scan with ARPES. This is the real space dimensions. And then this is zoom in. And so here the step is 50 nanometer steps with 120 nanometer resolution. And then for each pixel on this real space scan, then you can do the full three-dimensional measurement in momentum space of the band dispersion here. So this is a new mode that can be utilized. I'll say a few words about that in the next couple slides. And then Another development in the recent years is the uniaxial strain, in situ uniaxial strain, which is really driven by the discovery of pneumatic water in the iron pnictides here. And then finally, I think this is something we are interested in recently, is to add the possibility of doing ARPES under a finite, small but finite magnetic field. So I'll take some time to talk about each of these three things just to show you some of the stuff that people are working on. Okay. So here, this is, so for micro ARPES and nano ARPES, so there's been development. This is work from Eli Rotenberg's group at Maestro Beamline. So this is the nose cone of the electron analyzer. The hemisphere is back there. But basically, they can manage to focus the beam down to micron, which is micro ARPES is usually something like 10 micron beam spot. And then nano ARPES is sub-micron, so now maybe 100 nanometer spatial resolution. And these together with what's known as the deflector mode, basically in the past we had to rotate the sample relative to the analyzer to map the entire Fermi surface. But as you can imagine, if you have a tiny sample and then you rotate experimentally, that's your beam was going to walk on your sample and then you're going to lose the sample. But there's been development of what's called the deflector mode. Basically, you can use electrical deflectors without moving anything, just make sure that you're measuring different slices across this emission angle. And these two things together really enable the measurement of tiny, tiny samples. So here's an example of the very first in situ gating plus ARPES measurements on monolayer graphene. And so basically, the construct of photoemission ARPES means that we have to have an open top surface. We cannot work with dual gate yet. And the top surface, the sample that we measure, have to be grounded. And the reason for that is because you have beam coming in, you keep ejecting electrons. And remember, we have to keep this region field-free in order to preserve the information of the photoelectrons on their way to the analyzer. So the top has to be grounded. We can only do backgate. And also it has to be homogeneous and flat in the region covered by the beam. Otherwise, you will have broadening your momentum resolution. So in this construct, which is work done by Dave Cobden's group in collaboration with Eli Rotenberg, they put this graphene on top of HBN, which really provides the doping and also the physical flatness of the under the beam, and where they can actually measure. And then this is the first time they can see that with gating, in situ gating, they can measure dispersion. And since then, there's been many groups that has utilized this technique to measure exfoliated flakes and also gated 2D materials. So I think this is a very nice development in the field. And just for completeness, since a lot of people are interested in Moray, I think these two papers back to back were probably one of the first to measure the Moray mini bands, mini flat bands here. I won't go into too much detail, but here is in momentum space. You can see this is the Moray flat band seen at the Fermi level for twisted bilayer graphene. Okay, all right. And so the nice thing about having a small beam with photoemission is not just for 2D materials. It's actually very beneficial for a lot of us working in bulk materials as well, because in the past, we could only measure samples that are really flat, really cleavable. But now with the possibility of a small beam spot, we can measure samples that are very hard to cleave, samples that are flaky, samples that don't behave well physically, but actually have a way to look at some of the things that weren't able to be measured previously. I wanted to give you an example since this is a topological workshop, and I just wanted to show you one example that we have utilized the small beam for, and that is a measurement of a weak TI. So by way of introducing this, I think this is already somewhat covered in the past 2 days. We know that in 2D, you have one Z2 topological invariant, and then in 3D, there are 4. And so what that means is that a topological insulator can now, in 3D, be classified into either a weak TI or a strong TI. And to an experimentalist, this is my understanding of this. Basically, for a strong TI, you have odd number of band inversions in bulk. So what that means is that projected to every surface, you will always have not odd number of surface topological Dirac cones on every single surface. But for a weak TI, that doesn't happen. You will have certain surfaces that are topologically dark or have no topological surface states, and then on other surfaces you have topological surface states. So you can imagine really the way to distinguish these two is to be able to measure on a sample on multiple surfaces, because if you see a direct surface state, that you cannot really use that to make an argument which class it is, right? So for the vast majority of TIs that's been studied with ARPES, they're all mostly strong TI, and we're usually always limited to looking at a single surface. So it's been very difficult to identify this in 3D. So recently, I guess not recent anymore, there's this class of quasi-1D materials. You can, when they're grown, they look like this. So in the past, you really cannot think about measuring this with ARPES. But basically, this class of materials, bismuth halides or bismuth 4, either iodine 4 or bromine 4, these are weakly coupled one-dimensional chains, bismuth chains. And the nice thing about these is that this is basically the crystal structure. You can see that these are just chains that are stacked in both dimensions. So naturally, you can cleave the crystal either in this way, which will expose the O1 surface, or it turns out that you can actually cleave them this way. You can, which will tell you, which will reveal the side surface or the 100 surface. And these materials, when you calculate their band dispersions with DFT, without SOC, this is the band that's closest to the Fermi level. And these are bismuth p orbitals. And the size of this gap actually strongly affects whether this eventually becomes a weak TI or a strong TI. And the reason is the following. So this is what's calculated for bismuth iodide. This is what's calculated for bismuth bromide. If you include spin-orbit coupling, you will see that the number of band inversions can be different dependent on the size of this gap. And so for this top case, what you see is that there is one single band inversion which happens at the endpoint of the Brillouin zone. What that means is that if you think about the projection to the different surfaces, you will have a single Dirac surface state on all the surfaces. And so this would classify this as a strong TI. But if you imagine this is a different case, just slightly tune this band gap, you can actually eventually end up with two band inversions here at the L point and N point. And what this means is that when you project to the top surface, these two sort of annihilate each other, so you get no topological surface states on the O1 surface, and then you get two Dirac cones on the side surface. So this would be classified as a weak TI. So it's actually important to experimentally figure out, one of these two cases. Just make a point. So these materials now with these micro ARPES, nano ARPES, you can actually cleave on different surfaces and look directly at the electronic surface states on the O1, which is shown here on the top surface. We can see that there are no topological surface states. This is just a bulk gap, which is close to the Fermi level. But on the side surface, you can do the sample sideways. This is like a 50 micron size surface, which we can measure directly, see two topological surface states. And this is a direct way to actually see this is a weak TI instead of a strong TI. So this is an example of the type of things that's now enabled by micro nano ARPES and many others. Okay, so that's the first part. Second, I just want to quickly go over this technique, which is close to my heart, having grown up with the iron pnictides. So this is the ability to apply in situ uniaxial strain while doing ARPES measurements. So this really started because of the discovery of the iron pnictides superconductors. So this is the phase diagram, I think, already shown by previous speakers. What's interesting here is that you see this phase diagram. Here is our horizontal axis is doping. These are the superconducting domes. And then the parent compound lives in this region where there are a couple symmetry breaking phase transitions. So here in this white space normal state, this is a C4 rotational symmetric phase. And then when you enter this blue region, this is a collinear spin density wave order. So the spins order ferromagnetically along this axis and the antiferro along the orthogonal axis, right? So you can already see that this breaks rotation, that has broken rotational C4 symmetry. So what that means is that actually from some of the doping regime, you actually first enter a structural transition that marks a boundary of what's called the nematic order, where the rotational symmetry is first broken, and then enters this magnetic order phase. So this is a very interesting phase that's basically very universal across many iron nictide families, but the difficulty thing for experiments is that when the system breaks rotational C4, part of the sample will like to break it in this way, part of the sample will like to break it that way. So what that means is that for experimental probes like ARPES and other macroscopic probes, what we measure is sort of like the overlap of these two, so you don't really get any intrinsic information about the nematic order in here. So this really drove a lot of activities across different techniques to develop these kind of mechanical strain devices, uniaxial strain devices. And so this is the first, so this is really driven by Ian Fisher's group's work, where they developed this clamping device. Basically, you can glue your sample, press it along one direction, and then this will help the sample to prefer one orientation over the other, and then get a largely detwinned crystal, in which case you can measure all the intrinsic properties that you want. So we adapted this for photo emission. This is the initial kind where you just clamp it, and then these are independent developments by other groups, from Chang-Yang Kim's group here, developed by Yongquan Kim, and also this is the device from Donglai Feng's group back in the day. And using this, we were able to look at the intrinsic property of the nematic order. So basically, you can measure the band dispersions along the orthogonal directions. In the C4 phase, these actually represent the XZ and YZ orbitals, and they are degenerate. And then if you go into this into the nematic phase, you can see that they actually shift anisotropically. And the important thing is that the energy scale associated with the symmetry breaking in the orbital degree of freedom is quite large. It's 80 millivolts. You can compare this to the amount of energy difference you can actually get by only considering the lattice orthorhombicity. This is almost an order of magnitude larger than this. So this suggests that this phenomena of the orbital anisotropy cannot be driven really by the lattice degree of freedom, but it's really one of the driving forces of this order. Anyway, so this is the sort of early work putting strain. And then, so that's basically a way to look at on-off effects of strain. But then, also again, driven by Ian Fisher's group, folks have developed the way to actually apply continuously tunable in situ uniaxial strain by the way of using these piezo devices. Basically, these are materials where you apply a voltage, they will shrink or expand on demand, depending on how large a voltage you can apply. And then this is developed by Cliff Hicks and others, where they can actually have three that also account for the thermal expansion. And then basically, by applying voltage plus and minus, you can stretch or compress the sample and then do the complete series of measurement. This really enables a new type of measurement I will discuss in the next slide. But just to demonstrate this thing, this is my student's been working on this device for a long time. This is the one he made for our own group, following the leading work by these others. Basically, you can actually see that continuously you can change the domain population and then really in situ do the strain measurements. What does this give us? So the kind of measurement you can do with this kind of tunable uniaxial strain is the nematic susceptibility measurements. So basically, what you can do is, this is nice work by Yan Zhang's group at Peking University. This is really a very nice paper. What they have done is they can measure the amount of band shift in response to the strain for different part of the momentum space. You can see the linear response, and from this is measured around the gamma point, this is measured around the end point. You can extract the slope of this linear response, and that slope can be measured as a function of temperature. And so nicely, you can actually see that you can do this kind of a pneumatic accessibility measurements in a momentum resolved or orbital resolved way. And very curiously for this material, what they see, and make a long story short, is that the response is highly momentum dependent, right? So you can see the divergent behavior for the corner of the Brownian zone, but for the gamma point, for the center of the zone, it doesn't show this some kind of divergent behavior. So this actually tells us something about the type of the orbital order that's actually responsible for the pneumatic order in the iron pnictides. That means that because it has this momentum dependence, it cannot be a ferro-orbital type of ordering, but you have to have a highly anisotropic term. So just compare this to the more well-known measurement of the pneumatic accessibility from elastoresistivity measurements from Ian Fisher's group and Junhao Zhu. So this is the measurement of the difference in the anisotropy of your resistivity in the A and B direction. So you take the difference of the resistivity between these two directions, and then you measure that as a function strain, and then generate the slope very similar way, and then do that as a function temperature. You can see this kind of divergent behavior. This is one of the first evidence that this is an electronic pneumatic order in the iron pnictides from transfer measurements. But you can see now that if you're able to do this kind of continuous strain with photo emission, then you can actually have additional information about this with the momentum structure. So I think this is a very promising way to look at pneumatic order for materials beyond the iron pnictide. So something we're currently using this to look at the superconducting dome region of the iron pnictides to try to understand the effect of pneumatic accessibility near the superconducting dome. Anyway, so this is the second aspect. So the third one, I want to just, this is a very recent thing that we started to tamper with, which is magnetic field. As I sort of implied in the beginning, in the history of ARPES, everybody is very careful about shielding all of the magnetic field from the Earth and other labs, nearby labs, to make sure that the electrons that are ejected from the samples are unperturbed on their way to the analyzer. So usually, so this is why, even though the magnetic field is a very common tuning knob for a lot of probes, but not for ARPES. But recently, we started to tamper with this to try to see how much we can go with this. So my postdoc, Jiangwei Huang, he's just recently moved on, but he actually started to really bravely going into this direction. There's a lot of benefit, a lot of discussion with Professor Yu He from Yale also. He built basically a very simple, just put a solenoid around the sample, and we have a way to run current through our sample stage, and then you can imagine if you continue to tune the current, you can get an out-of-plane field at the sample location that can be tuned in this dimension. And so he did some characterization of what this would look like. You can vary the current. We're limited to this range, and then you can measure the amount of field we can have at the sample location, which for now it's about 10 millitesla. And then he can also measure. We also have to understand what are the extrinsic effects on our photoelectron before we sort of look for real physics. So that means we need to understand what actually happens in this region. So this region defines the extrinsic effects that we need to first understand from on our photoelectrons. And so this is the decay of the field above the sample. And so he did a lot of simulations of finite element analysis, trying to understand what are the extrinsic effects on the photoelectrons emitted. And then if we can have a grasp on those, then we can back out what is the effect on the electronic state before the electrons were ejected. Right? So basically, you can imagine if you have out-of-plane field, the first order of business is that there is a Lorentz rotation. So the electrons that enter the analyzer slit will look like they're rotated. And so he did a bunch of simulations to look at the rotation for different emission angles. Emission angle is the angle at which the electrons come out of the sample. And then you can see that they actually happen in a parallel fashion, which means that the entire Fermi surface, doesn't matter which emission angles you have, basically rotate together. So that means this is a manageable way to, you can fix you can reverse this effect in your data analysis. So I want to first show you a couple extrinsic effects that we have learned, and then show you maybe one slide about the real material we have measured with this technique. So there are three extrinsic effects that we have seen. Again, these are effects that are not directly on the electronic states, but just in this region where we have modified, we need to figure out how to reverse these effects to figure out what is the initial state from the electron, where the electrons were ejected. So we tried on bismuth selenide, and this basically these are constant energy contours taken here below the Dirac cone. And as you crank up the current, you crank up the field, and then you see naturally there's a Lorentz rotation, and this is actually a nice way to actually tell us exactly how much field the sample actually experiences. And you can see that actually is a linear behavior as expected, so we can, this is the effect that's easy to reverse. The second effect we see is we measured on the iron nictide, and you can see the rotation first, but there's also a contraction of the emission angle. So this is a natural photo emission cone, but the electrons that we measure under the field are contracted. And I don't want to go into too much detail about why this is, but if you're interested, you can read this. But this is another thing that's easily manageable in our data analysis. And the third one, just want to caution a little bit. We try to look at, what is the effect of magnetic field on bismuth selenide. So this is without a field, and when we first added the field, we saw, the Dirac cone is gone, which is kind of interesting. But Jianwei, being the really careful guy that he is, really thought deeply about why this is before jumping to conclusions. And we realized that this is actually due to a trivial momentum broadening effect. Just a word of caution for those of you who want to use this, want to explore this technique. Basically, he realized that when we apply a field, even though the energy is unperturbed under a magnetic field, but there is a broadening of the momentum in the momentum direction of the spectral weight. And because these cuts are taken in these slices, the momentum broadening happens in all directions isotropically, with both within the plane and also in the perpendicular direction, right? So what that means is that some of the spectral weight from the Dirac point actually gets spread out to the direction perpendicular to the slice. So that's why if you look at the EDC here, the energy distribution curve, you see the field sort of looks like it's like making a dip, but actually this is really due to this. So to prove this, he showed that if you take a simple broadening of this in isotropically in 2D, then you actually get the spectra. So just a word of caution, when we want to look at these kind of effects on the Dirac points, we have to take measurements in the three directions and then really account for all the spectral weight before we. Anyway, so these are the sort of the trivial effects we now understand. So what is this good for? What have we looked at? I'm going to show you one example. And this is the material, the famous material that Stevens talked about, and then also, I guess, Vidya will also talk about tomorrow. And this is the Kagome system, cesium, vanadium-3, antimony 5. And it's interesting because already Stephen has gone over this. It has a charged water that is associated with a chiral flux state. So there are these potentially loop currents that breaks time reversal symmetry. And many probes have seen an effect that's associated with the time, that suggests time reversal symmetry breaking. So for example, this is the μSR measurement that Stephen has mentioned. That there you see the change, the onset of the CEW, and then change in the relaxation rate of the muons. And then this is the magnetotransport measurement under a field. There has an odd in-field effect. And then this is, I will leave video. I'm happy that she will talk about this, so I won't spend too much time with this. But they see that the CEW peaks as they get from the Fourier transform has a chirality by the height of these peaks, and that chirality changes depending on the sign of the magnetic field that you apply, right? So this seems like an ideal material that seems to be really responsive to tiny field. So we put this to the test. I'm going to show you unpublished data. So we look at this material with the field. We compare the no field, plus field, and minus field. And just to show you some of the effect, you can see this is a measure of the Fermi surface. This is a measure of the constant energy contour taken about 350 millivolts below the Fermi level. What you see here, this is the Brillouin zone. These are the sort of triangular sheets that are associated with this Van Hove singularity. If you stare at this long enough, you'll notice that under zero field, these two, the bands at the K point and the K prime are very similar. If you apply even 1 millitesla, what you see is that these remain sharp, these are broadened, are disappearing. If you flip the field, you see that these remain sharp, and these are broadened. So there's a flipping, there's some effect which is odd in field. To see that better, you can take 2 cuts and look at the energy dimension, and that cut 1 is up shown here, cut 2 is shown here. This is the crossing point, this is the end point between the top and bottom K and K prime. And so if you take the subtraction of these two plus and minus field, which is shown here, you can see that this is the part where the minus field is higher than the plus field, and this pattern is actually reversed when you go from this side of the zone boundary to this side of the zone boundary. So this definitely tells us that this material actually does have a very strong response to even a millitesla field. So I think this is very promising. We haven't. Hopefully we'll have something more detailed to show you with this, but just to demonstrate that we're starting to see some interesting intrinsic effects by measuring ARPES under field. Okay, so this is a totally independent effort at implementing magneto-ARPES. So the phrase of magneto-ARPES is really from Eli Rotenberg, who's at Advanced Light Source. And this is their device, which is a way to apply in-plane magnetic field at the sample location. So this is their device. They make this yoke shape with a cut. This is I think iron core, and then there's a cut in the middle, and this is where the sample will be glued. And then they did simulations of how high of a field they can actually achieve at the sample location. And according to at least this construct, this is 60 millitesla at the location of the sample. Of course, this is the in-plane field. This is different than our design, which is out-of-plane field. But I see this is another. There are many other ways to think about how to improve on these devices, and I think this is really a wide open field. So what are we going to work on next? So in terms of instrumentation development, the important thing really is to maximize the field strength at the sample location at the same time, minimizing the field between the sample and the analyzer. That will reduce the amount of extrinsic effects we see and then increase the amount of intrinsic effect that we will see. So I think multiple groups are working on this now, and hopefully there will be more designs of these devices coming out in the near future. And theoretically, I think it's also interesting to start thinking about what one would expect in this process. And so anyway, so I think if you're interested, I think this is an interesting development. Okay, so that's the first part. Any questions? Oh, we'll go to the, yeah.
You have said, if I understood correctly, that you still cannot double gate. Do you think it would be possible to do ARPES with a double gate?
Not that I don't think right now it's possible because we need the electrons to come out in a field-free region. So I think that's the difficulty at the moment.
Possible one day?
I hope so. I think.
It's difficult, right?
Yeah. I don't know. Maybe there are many more smart people out there. I'm sure one day maybe that's possible if you have a way to dig a hole in the top, a way to shield the field in the region where the electrons come out. I think that's the only constraint. So all the smart people sitting here, I think maybe one day this is possible. Yeah. Yes.
So one thing that I don't understand about ARPES, among the many things, what determines whether you can look at other places in the Brillouin zone? So sometimes, for different, I guess, materials, or I mean, you told me, but sometimes you can look at the gamma point. Sometimes you can look at outside of the gamma point, but sometimes this is hard.
Yeah.
So what determines whether you can or you cannot go and scan the whole Brillouin zone?
That's a very good question. This depends on the photon energy. So if you have like, I think what you're probably thinking about is like with the laser ARPES, if you're a 6, 7 EV, after you overcome the work function, you have about maybe one or 2 EV left. That's the dynamic range for the amount of kinetic energy you can measure. So that limits you to the zone center for most materials. But if you use a synchrotron where the photon energy is high, like 20 EV or above, then that you can measure the entire first boron zone or even the second, third out there. Yeah, so that's the ultimate limitation on how much you can measure in momentum space.
Thanks.
That's an excellent question. Okay. Yeah, yes.
Thanks for the pedagogical talk. I was wondering, when you're looking at your twin sample, where you have like these different pneumatic domains, what would you see if you measure ARPES? Would you see a superposition of like both Fermi surfaces, or like both Fermi surfaces of each pneumatic state, or would you just see mesh?
Exactly, you will see the overlap of the two. If you only have 2 domains and not more, your signal will be just a direct like adding of those two, modulated by the amount of domains.
So just like see like, okay,
Yeah,
then
we
you
see
would like
this
see
piece
C4 symmetry again,
Yes.
but just because of like both states.
Exactly, yeah.
Okay,
yeah.
thanks.
Thank you. Cool, thank you for all the questions. So for the next part, I'm going to talk more into how we use ARPES to look at bulk materials that exhibit flat bands. And I think this topic has already been discussed quite a lot, so I will take that benefit and tell you a bit more along that line. So I think over the week, we already know that to get to the flat band regime, there are 2 energy scales that we care about. One is the Coulomb interaction U, and then the bandwidth or the kinetic energy. And then the U has to be much larger than W to have a flat band. But I think there were some questions, but there are different ways to get there, right? So one way is to crank up U, and the other way is to reduce W. And so in the way to crank up U, so they actually produce very different types of flat bands. So if you crank up U, this is very nice. I just pulled this out of this very nice paper by a lot of people sitting here. Basically, what you would see in this case is that the linear functions will be localized on atomic sites. There's no overlap between them, and this is the limit that's driven by Coulomb interactions. On the other limit, we have also seen a lot of examples by Stephen's talk and also later talks too. You can quench the hopping using special lattices, and you can see that the block wave functions now no longer sit on the atomic sites, but they're somewhere in the middle, and they're actually kind of large. And there is overlap, but the hopping is actually is quenched by the destructive interference of the electronic wave functions. So these are fundamentally distinct, and so from a spectroscopy perspective, they also look different. So I'm going to show you some examples of what they look like in experiments. Let me first talk about the left-hand side, so the large U limit. And I think there's really benefit from Lenny's talk. One of the very clean example is the heavy fermion system, which has been discussed quite a bit. So you can imagine you have a system with localized moments. They will contribute nothing near the Fermi level when they're not interacting with the conduction SPD electrons, right? This is this limit, and the dispersion you will see is just the dispersive band from the conduction electrons. And if you turn on, for example, Coulomb interactions between the localized moments and all these conduction electrons, then you start to see the flat band in the form of hybridization between the flat band and the dispersive band. So the bands you will see are like this guy and this guy. So then you start to see some spectral weight from the flat bands. And then your size of your Fermi surface under this construct will also change. So this has been discussed, and I want to show you, and I really am motivated by this figure that Lenny has shown. I'll show you some of the stuff that we can see related to this in a slightly different material system, which is the iron-based superconductor. So just a reminder, so this is what you would see when you have start putting interactions. So this green stuff, this is peak in the middle at the Fermi level. These are the quasi-particles, and then these are the lower upper Hubbard bands here, right? And so if you take one of these moderately correlated material, and you take a large energy range map, ARPES spectra, a lot of stuff happens, but if you integrate along this dimension, which is shown here, you will see essentially something like a measure of a density of states. You got all these quasi-particle peaks close to the Fermi level. That's basically the stuff. And then if you go higher up around 2 eV, there's the hump, which is this, sorry, I don't know if it's showing up on the screen, but you can see a band here. That's the lower Hubbard band. That's essentially similar to this stuff here, right? So you can actually directly see this with photo emission. And what's interesting about this system is that the iron-based superconductors are multi-orbital systems. They have more than one band, more than one orbital. So really interesting stuff happens near the Fermi level. So I'm going to take the next couple slides by zooming in very close to the Fermi level. So this is 1 eV, this is 100 millivolts. And this is what happens in that region. So this is cuts taken on iron, tellurium, selenium. You can vary the amount of selenium versus tellurium. That's a tuning up in this family. It's isovalent. But what you actually see is something interesting. So near the gamma point, this is energy versus momentum, you see 3 whole bands, right? And then if you tune the amount of selenium from one end to the other, what you see is that the curvature of these 2 inner bands don't change very much. But this outer one actually visibly changes from one end to the other. And the curvature, as you know, is related to the effective mass. So you can actually extract that directly by fitting these bands. So for the inner 2 bands, their mass enhancement, so this is the effective mass divided by the mass you get from the DFT calculation. This is mass enhancement. And for the inner bands, they don't change, but for this one, which happens to be XY orbital, you can see its effective mass enhancement actually diverges towards this end. This is iron tellurium. This suggests that these orbitals, like Lenny has discussed, actually exhibits orbital-dependent correlation effects. So how to capture or understand this is a collaboration or calculation with my colleague Tim L.C.'s group. You can see that in the strongly correlated regime, this is the XY band. It's already very strongly normalized near the Fermi level, and it's very faint, but it still has a finite hybridization with other dispersive states. If you keep going towards that end, they can realize a regime. Theoretically, we can argue whether that's reached or not. But anyway, from this calculation at least, they actually see a limit where that orbital becomes not localized. So it's gone, it's gapped out from near the Fermi level. And then you recover the Fermi surface you would get from this dispersive states. And this is the calculation comes out of this safe spin calculation. You see that without any symmetry breaking phases, you actually see the Fermi surface shape change. And that's exactly what we see experimentally from photo emission. We see the small pockets on this side, and then these large things on that side, which actually indicates that the system, actually this band becomes extremely flat, but it loses all spectral weight. So this is one type of flat band by cranking up U. And then I think Lenny also mentioned that as a function temperature, you should also see some disappearing of these quasi-particles, and indeed we see that. So if you take one of these guy over here, and then which is shown here, if you crank up the temperature, this faint band actually disappears. All of its quasi-particle disappear from near the Fermi level, along with the hybridization with the dispersive state is also gone. You can track, without going into too much detail, you can track how this spectral weight disappears, and this tells you that as a function temperature, that quasi-particle of that orbital goes away, right? So that's an example on the left-hand side. This is what happens when you have a Coulomb interaction-driven flat band. It's renormalized to the Fermi level, spectral weight goes away, and I'm going to want to contrast that with the right-hand side, which is the kind of flat band you get by quenching out W. So I won't. Stevens also talked about this for Kagome systems. You have this destruct interference. I'm going to go really quickly. So this is the example he discussed. Cobalt-10. These are the flat bands, topological flat bands you get from the Kagome lattice. And you can see that all of these bands, in contrast to the case of a U-driven flat bands, have full quasi-particle coherence. You can see them with your eyes. And of course, they could happen anywhere in energy depending on the fittings, right? So that's another distinction with the type of U-driven flatband. So that's the two cases, and just okay, thank you. So I will stop after the slide. So and even though there are differences, and we have seen that it's actually very useful to sort of map them onto each other. We've seen Zhidao talk about this yesterday, his construct with Andre Bernovic about how to map these topological flatbands onto the heavy fermion model, where you have the localized states and the dispersive states, right? I'm sorry, this is not a complete list. There are many others that work on this. I just pulled some examples out just for a quick slide. There are other ways to construct this. This is the model by Chimel's group, and basically they group together the flatband with the dispersive band that it touches, and take those together as what they call the compact molecular orbitals. And then with this construct, they can again map this to their Kondo phase diagrams and actually see the similarities between them. So. I will just show you the outline for the second half. So what I'm going to plan to do to show you in the second hour is to talk about different ways to, there will be halves. The first half, I will talk about different ways to construct these geometrically frustrated flat bands in 3 cases. And then for the second half of the second talk, I want to also talk a little bit about what we can learn from spectroscopy about the role of these flat bands in bulk materials for magnetic orders. So I'm going to show you some data on 3 examples where we actually see the flat bands do stuff. And we haven't been able to see that in twisted bilayer or Moiré systems yet, but hopefully we can learn something from the bulk states where we can image and learn about what is the nature of the magnetic order associated with these flat bands. So that's what's going to come in the next hour. So thank you.
Any questions?
I guess we can discuss in a coffee break, I guess.
Yeah. I have a question.
Oh, okay.
For the ARPES, the magneto ARPES, what do you anticipate, like the upper field line would be? You know, these are pretty small fields that you're able to implement.
Yeah. There are some simulations where you can get maybe like tens of millitesla at the moment, and still, I think the key is to, if you can confine the field to just the sample plane, then there's no upper limit, right? Like, I think that just the only thing that limit us is basically the extrinsic effects that will broaden our spectra to the point where you cannot see anything meaningful anymore. And that happens in the spatial region between the sample and the analyzer. So if you have ways to confine the field to just the sample plane, then I think, at least in principle, there's no limitation. So I think it's just the beginning. I think quite a number of groups are working on the next generation devices. So I think there'll be exciting opportunities for if you're interested. Yeah.
If there's no other questions, we'll thank Ming again.
Thank you.